All right, so let's get started. Graphs of function. So this is what I call just a menagerie of function. And so it's just to use all the different types of functions you're going to see. And so if you look at a graph, you look at an equation, you can tell what the graph should look like. And if you look at the graph, you should kind of tell what the equation looks like. So this is just something just to get used to and see. I think it's a very useful section, even though we don't teach you very much math per se. Um, Anyways, so a function is a graph of all the order pairs. We already talked about it. The main point of this section is to get familiar with graphs. So here, if I have y equals 4, we're just going to count up 1, 2, 3, 4, and draw a line. Okay. Here, as we did this before, here, one last thing so I have it ready to go for you guys when I want it. Boop, boop. All right. Here, so we did this last time. So here's another way of looking at the standard equation. So here, if I want to find the x-intercept, so the x-intercept of here, if I have, if y is 0, x better be 4. 1, 2, 3, 4, because 4 times 3 equals 12. And if x is 0, y better be 6. So right here, I'll give you a hint. All these are 8 by 8. So for the 6, it's easier just to count down to, right? And so here we can draw in a straight line. Maybe if I can get vaguely close to drawing a straight line. Nope. That's better. That's good enough. All right, so these are straight lines. So here we have x squared. X squared, here if x is 1, or x is 0, we have 0. If x is 1, we have 1. Same if it's negative 1. If x is 2, we have 4. Same if it was negative 4, or negative 2, it would be positive 4, because negative 2 squared is 4. Next here is at 9, so up above where we're at. And this is a quadratic, and I assume you've seen something like this before. All right. Here's the cubic. So let's just do some points. So if x is 0, y is 0. If x is 1, y is 1. When x is 2, y is 2 cubed is 8. When x is minus 1, we have negative 1 cubed, which is negative 1. So negative 1 times negative 1 times negative 1 is negative 1. Negative 2 cubed would be negative 2 times negative 2 times negative 2 is minus 8. So if you don't know what a graph is, just make a bunch of points and just connect them. And so here it looks like this, 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 and down here and up here. So it comes in pretty strong and goes out like that. So this is what x cubed looks like. All right, I'll leave that for a second. Let you guys copy it down. Even though this section is 4 pages, it will not take us long to go through it. All right. Let's go to this one. All right, so let's look at, oops. All right, so here we want to sketch the graph by plotting points. So here we have x to the 5th and x to the 6th. So let's just plot some points. So we have 0, 0. We'll have 1, comma 1, negative 1, comma negative 1. But here, if we put in 2, this is already at 32, right? If we plug in negative 2, this is already at minus 32, just because negative 2 is there. Before we actually draw in, let's actually do, let's draw the points. We have here, here, and here. Instead of being over this way, it's just a lot more like this, which there we go. So it's a little bit sharper. I know this is hard to see right here. That's why we're going to pull up decimals in a second. And then here we have 0 and 0, 1 and -1 or -1, 1 and 1, sorry, -1 and 1, getting ahead of myself. And then 2 and 64, and then 2 and -2 and +64 again, because if I take the 6th power. And so here this looks strangely like this. So this begins to, so these tend to mimic each other. And so what you can draw from this graph, from this, is that these should have a little bit more space in it. Let me put a little line here. So odd powers of x, such as x, x cubed, x to the 5th, all tend to look the same. And we're gonna graph each one of them here. So x, oops. So here is x. Grab this, and we'll do x cubed. I'm gonna grab a different color here. Well, let's grab this too, I suppose. X to the 5th. And so it just gets a little bit sharper and sharper and sharper. Well, x, oops. I wrote squared, but I didn't want to square. Well, x here, what's that? It's the same thing with the even power. So x, so have x squared. So x squared looks vaguely like this. It's going to be a little bit, x to the 4th will be a little sharper. And then here, if I did like x to the 6th, it's even sharper still. Okay, and I want to show this in Desmos. So kind of make some sort of sketch of this. But this is much easier seen in Desmos. So here, I'm going to display that for you. All right, so let's have x. We're going to have x to the 3rd. We're going to have x to the 5th. And then we're going to have like x to the 31st. That way you get a whole bunch of them. I want to kind of zoom on in here. All right, so notice here when we hit like x to the 31st, so x technically is an odd power, has no bend in it. Let's get rid of that one for a second. And then let's look at, this is just x squared, kind of bends and curves and goes up. So it looks like kind of like x squared, and then it looks like minus x squared a little bit, right? And then here, when we put in the x to the 5th, it's a little bit sharper. And then x to the 31st, it's very sharp. And so let's look at the difference here. Here, it's like not 1, not close to 1, not close to 1, gets bigger, 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 and then hits 1 and just explodes, right? And so the greater the power of the odd function, the odd function, or the odd polynomial, the sharper this will look. And so given x, because now in your brain, you could probably predict what x to the 9th looks like, right? It's going to be somewhere between the blue line and the purple line, right? And you're right, it is. And so that's just to get you an idea of what all powers of this. Now, when we start messing with it, right, adding like plus 8x to the 8th, right, it's going to start looking, massively different, right? It's going to have ups and downs and all that stuff. We're not going to worry about that. We're just looking at clean powers right now. And the same is going to be true for our squares. So here we have x squared, our even terms, x to the 4th, x to the 6th. And so notice here once again, we get sharper and sharper, right? And so it comes more and more into itself around 1, right? So here's our 1, right? And you could probably predict what x to the 32nd looks like. Well, x to the 32nd, oops, let's just do the 34th, I guess. Boop. And notice how it looks really exaggerated. It's all the way at 1, it flattens out, and then goes up. And that makes sense, because anything less than 1, the more I multiply it by itself, the smaller it gets, right? Anything greater than 1, the more I multiply it, the sharper it gets. And so here, as the powers get in, it gets more and more like this box right here. Just like, okay. So hopefully that makes a lot of sense. And so that should be able, so here at the end of this, you say, okay, given any power of x, I can vaguely picture what it is in my head. All right, so let's do some square roots. And then once again, we'll do some square roots and decimals so I can show you some things. And then, all right, so let's do the same things. All right, so here, let's do some square roots. So I'm gonna, oops, I'm still in like light blue. Let's go back to our darker blue. So from 0 to 0, 0. If I plug in 0, I get 0 back. If I plug in 1, I'm gonna get 1 back. If I plug in 4, the reason I'm gonna choose 4 this time because I get 2 back. It's a nice even number. If I plug in 9, I'll get 3 back. And here, if I plug in -1, I get undefined, right? So I don't get a point. So this is not really a point. So not really a point. Okay, so this one's not really a point. But so here I start at 0. Put a nice little thing in here. At 1, I'm at 1. At 4, I'm at 2. And then at 9, I'm at 3. And so I have, this is my graph. Notice here, and I'll go ahead and do it in a different color. Notice this is outside the domain. I guess I should have done this in a lighter, a little bit darker color. So that's all. This is outside the domain. There's nothing here, right? There's nothing here. It's all outside the domain. But let's do the cubic group. Here at 0, I have 0. Here at 1, I'll have 1. But here I can plug in a -1 because there is -1 cubed is equal to -1. And so that's okay, right? And so 8, well, if I cube 2, I get to 8. So whatever that. But if I have -8, I can cube -2. And so this one, for the odd powers, everything's in the domain. And so here I can just quickly draw that in. And notice here that this looks a lot like this, just kind of knocked on its side and flipped, right? All right, I do want to show this in Desmos. So I'll give you a second to copy that down and I'll get Desmos ready. That way you don't have to wait for me. Can I type in? No. Fine. We're gonna do this. That's what I'm gonna do. Hi, you work because I ask you to. Be that way. I guess that works out. Woohoo! Okay. All right. Actually, we're find a timer copy. So let's look at this. So here, if I have, notice here that these are, this is a square root. This would be the same thing if I wrote 4 radical, where the 4 is that. So I have the 4th root. And here, if I have the 32nd root, and I draw that in, notice it follows the same pattern, it just gets sharper and sharper and sharper. The same thing with the cube roots. So if this was cubed, this was, say, 7, and say this was 35. Notice here they just get sharper and sharper and sharper. Okay. And so they all follow the same format. So you know what the graph of any root to any power now. You can safely think in your head what the graph looks like. Okay. All right, so let's do the next page. Boop. All right, so here we're going to sketch more things by finding points. And so once again, if you don't know what these look like, we're going to just drop down points. I'm going to change the scale on this one. The next two to be 2, so this will be 1, this will be 2, this will be 3. just because the pictures come out a little bit better for us drawing them. So this will be 1, this will be 2, this will be 3, just to keep the same sort of scaling going along. All right, so here, if I plug in 1, I get 1. If I plug in 2, I get a half. If I plug in a half, I get 2. And if I plug in minus a half, I'll get minus 2. And if I plug in 2 or minus 2, I get minus a half. Okay. So here's just a bunch of points I plugged in. And so what this ends up working out is 1 and 1 is a point. If I plug in 0, I get nothing, right? So once again, this is undefined. And so I can't actually plug in that point. Let me do -1 gives me -1. 1 over -1 gives me -1. So at 2, I'm at a half. At a half, I'm at 2. And so see how this makes this graph a little bit easier to draw. Wahoo. Wahoo. There we go. All right, and so this is what the 1 over x looks like. I'm going to do the same thing over here with 1 over x squared. So 1 gives me 1. -1 gives me 1. 2 gives me a fourth. That's 1 over 2 squared is 1 over 4. -2 gives me a fourth, and so forth. And so here we have our 1 and 1s, but this time it's right here. Notice here that 0 gives me nothing. I cannot plug in a 0. So here at a half, I'm all the way up top. And then here at 2, I'm pretty much already down to a fourth. So it comes in like this. Okay. All right, I'll let you guys draw that, and I will display something on Desmos. Desmos, I need 1 over x. Thank you. And I need 1 over x to the 5th, and then 1 divided by x to the 31st. All right, so let's look at this in Desmos. So here, zoom on in a little bit. All right, so here at 1, we have, let me just look at it. So here's our normal. And notice as we increase our x, this just gets sharper and sharper. And so here we can see. And so 1 over any power of x, any odd power of x is going to look like this. Now, if we make these even powers, I really wish somehow I could track that you guys just went in and messed with this and just type in some stuff on your own, because that would be better than doing the homework. Would be just playing with Desmos, going, oh, this is x is 6, this is x to the 30th, and you get a better feel for what's going on. So 1 over x to an even power will look like this. And notice how it gets sharper until it gets really sharp. And here you can see it just gets really sharp like that. Okay. And so with this, you now should feel comfortable. It's like, okay, I now know what everything looks like, right? Or a lot of the normal functions you'll see look like. All right, so let's look at some other graphs, just do some other things. And then we'll get into what is and isn't a function. All right, where we at? Whoop. All right, so here, this is the greatest integer function. So this is the greatest integer that is less than or equal to the x value. Okay, I know this is a different function. I know this as the floor function. The other function I know is the ceiling function. But I'll get into these after we do this. So here, let's do this. So what's the greatest integer that is less than or equal to 0? Why, it's 0, right? What's the greatest integer that is less than or equal to 0.5? Well, 0 is the greatest integer that is less than or equal to. So 0 is the greatest integer. What about 2.7? Well, that'd be 2, right? But here in chat, what's the greatest integer that is less than or equal to 1.5? So this is the first time I want you guys to respond. What's the greatest integer that is less than or equal to negative 1.5? So we have a guess. It's a good guess. We have another guess. It's a good guess. Okay, so yeah. So we have a couple guesses. 0. All right, so for those who made guesses, which I'm really happy you did, because um, here the greatest integer that is less than or equal to x. And so here, when I first did this, I put in -1. I'm not going to lie to you. I was like, oh, it's -1. You're throwing away whatever the decimal point is. But the -1 is actually greater than 1.5, right? So I made that mistake. That was the mistake I made. And I was like, no, wait a second, it's -2. And so you have to go down the integer to do that. And so if I was going to graph this, let's do the same. Let's do the same sort of scaling. Let's do 1, 2, 3, right? 1, 2, 3. So here at 0, it is 0, and every number from 0 to 1 up to 1 is also 0. And here, the second I hit 1, 1 is the greatest integer, and then all the way. We call these kind of step functions, where they kind of step up. So it's always something, then it goes up, always something goes up, always something goes up, right? Or down, or around. And so this is what this graph looks like. And it's kind of an odd looking graph, right? But here, and so for our 1.5 example, which would be right here, the greatest integer that is less than that would still be -2. Okay, does that make sense? Now, I've seen this in a lot of pre-calculus textbooks, but once you get into numerics, you usually do one of these two. We call this the floor function or the ceiling function. The floor function is exactly like the greatest integer function. You go to the lowest, you go down to the lowest integer, and sometimes you go up to the higher integer. Okay. I think in programming they have something like this. These functions exist in programming for some silly reason. Or not for some silly reason. There's very good reasons they exist in programming. Because let's pretend you're making a cute little RPG and you like hit somebody, right? But you have a complicated math formula, but you only want to give whole number little things, right? You only want to give whole number, powers to when you hit somebody. I mean, that's a video game reference of why you would want to do it. And in a video game, you probably use the ceiling function. You probably round up just to make you feel better about life, right? um, but there's other reasons because some functions can only accept integer values at all, right? So if it's not an integer value, some functions in your in C++ just won't work with it, right? And if you pull in an integer value, you have to convert it over to a decimal. So in programming, 1 is massively different than 1.00. These are massively different things, right? They are. So just things to be careful when you get I mean, you will do a little programming as engineers at some point, or at least have to touch it. That's a good thing to know these things. All right, so let's do this real quick. Here, for any piecewise function, you just graph. Here we're just going to graph x squared up to the point where, oh, and this is including, so this would be my solid dot. And so here, when x is less than or equal to 2, I graph x squared. And this is badly graphed. And then from here, x minus 2, so minus 2 to 2. Come on. Why is it not doing it? Ta-da. There we go. And so here, if you have a piecewise function, let me make this, I'm going to graph this a little less badly. Make this a little more of an open circle. It's a nice open circle. There we go. Okay, so for piecewise functions, when you're graphing it, once again, the arrow means it continues that way, right? So x squared does go beyond but what I've graphed here. It's just so I'm going to draw this and this. So you just graph this function all the way up until you hit 2. Here it is equal at 2. Notice here we have the equal sign at 2, so we make a solid dot here for x minus 2. Let's start here. So here, if I kind of drew in the rest of this graph, this is the rest of my line, but I only draw in the line from 2 where x is 0, because when I plug in 2, I get 0 here. And then here I have a slope of 1. So that's all you have to draw in for piecewise. Okay, I'll let you guys use that. All right. Let's do our last page. All right, so how do we tell a function? So in a function, we're going to use what we call the vertical line test. So a function, remember a function for every input, it has a unique output. So I can't have one. So one thing a function cannot do is I cannot plug in f of 1. If f of 1 goes to 2, f of 1 cannot also go to 3, right? That's what it means to be a function. For every input, there is a unique output. Now, it doesn't mean for every output there's unique input, right? Let's just take x squared for an example. F of x equals x squared. This is a function. But here, if I plug in f of minus 1, I get 1. And if I plug in f of 1, I also get 1, right? The outputs definitely do not need to be unique. But the inputs, if I have a unique input, if I have the input, a single input gives a single output. And what does that really ends up boiling down to for us? I guess I could leave that. So this is not a function. Okay. So how do we do that when it comes to graphing it? How do we tell looking at a graph? Well, here let's just draw in some random function. All right, so this is a random function, and it is a random function. And I'm going to grab, you know what? I'm going to choose a color. I'm going to choose light purple. Just for fun. So here, if I take vertical lines, that's a little too light. Let's make it kind of maroon. There we go. Here, if I choose this and I come down, I only intersect, no matter what vertical line I draw, I only intersect the graph once. And so here, I only hit it once. And so that means it passes, and this passes, and therefore is a function. Okay. Here, let me draw something that will definitely fail it. Yeah, that will fail, right? So here, if I draw a vertical line here, sure it passes, right? And here, if I draw a vertical line over here, sure it passes, right? But here, if I draw a vertical line right here, here I intersect it once, intersect it twice, and intersect it a few times. So this fails, right? And so notice, so this is not a function, not a function. And this is a function, at least as far as we've tested it. I can spell function, F-U. Okay. And notice if it fails in one place, in one line, the whole graph fails the test. Kind of like if you're taking a driver's test, you hit one card, you failed your entire test, no matter how well you did everywhere else. Maybe that's a terrible example, but so if one vertical line test fails, it just fails, right? It's just done. Okay. But if one vertical line test passes, it doesn't mean it passes. It has to pass for all vertical lines. So you just test a bunch of points. Please note, I have a note. I don't need no note. I need note. Get rid of this. All equations are not functions. Wow. I wrote this one while I was asleep, apparently. No, all equations are not functions. And let me show you two examples. Here we have a circle, right? We have a circle centered at x equals 1, y equals 0. So it's centered right here. This is the square root of, so my radius here is the square root of 3. So that'd be about here, 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 and here. And then if I drew my little vertical line, notice how this does not pass, right? So this fails. It is not a function. Apparently my brain's just a jukebox today. You guys ever listen to Rosa Schoolhouse conjunction, junction, but your function? Anyways. Oh man. Your professor's not sane today. All right, so let's look at this. How would I graph this? Does anyone know how I graph this? We probably just go to Desmos and see if I can make it to do it, right? I don't even know if Desmos would be kind enough to do this to me. Desmos. Can I borrow you? There we go. Whoop. Hi, Desmos. I want to graph this. It's not really, I want to say, it may be able to. It flat may be able to. I do not know. I am going to test it right now. X cubed minus 3 y squared. Oh, it can. I am proud of it. This is my function, right? Or not, this is my graph of my equation, right? If you did not know how to do this, what I would suggest doing is you say why you graph this equation. And let me show you this on Desmos before I do it live on the paper. What I would do is I'd graph this equation right here in whatever graphing. So if you eventually we will go back in person, and then you'll just have a graphing calculator or something. And you need the graph of this, but you only can plug in y equals something. So graph this and just reflect across the y equals x axis. So here just reflected across this axis, and you can draw it in. Okay, so that's a trick. So if you have x equals some y, graph the y, or graph it as x, and then just reflect it across the axis. Okay, so that's one trick of how to do this. So technically, you know how to graph 1 over y, 1 over y cubed, because all of this, if you just reflect it across the x, this y equals x, right? You know exactly what the, well, not the graph, yeah, the graph looks like, right? Looks like a spade card. Yeah, kind of does. So yeah, so that's how you do that. So, but right here we have this graph. So we're just going to copy over this graph. It comes in, it goes about 4, 2, 3, 0, 3, and 0, 0. So we'll just use those points, right? So we're just going to use those points. All right, so here we have 0. Hold on, I forgot what those points were. -4 and 2. -4 and 2 and 0 and 3, and there we go. So we'll just go All right, so that's roughly our graph. But notice here, this fails and it's not a function. Okay. Ta-da. All right.